Hi, I'm Firuza Yanchilina. Today we'll take a closer look at the third era in Schwarzschild solution. As a reminder, we've already explored the first two eras in previous videos. What if the foundation of modern gravity begins to crack precisely where we are used to setting its greatest triumph? Richard Feynman considered the singularity in Schwarzschild's solution to be a serious problem. And he was right. A singularity is nonsense within an equation. In physics, things like that are taken as a clear indication that a theory is either incomplete or incorrect. But something strange happened. This law didn't receive the attention it deserved. More than that, its consequences were turned into a kind of cult. That's how black holes with their paradoxical event horizons came into the picture. Yes, black holes are nothing more than errors in Schwarzschild's solution. What did you expect? Real objects discovered by astronomers through their telescopes. It's time to come back down to Earth. Black holes don't exist, and they have not been directly observed to this day. Black holes are errors in Schwarzschild's solution. This is not an emotional claim. It is a direct consequence of analyzing the equation. It's important to remember, Einstein and many experts in general relativity viewed singularities very negatively. Real physics shouldn't allow mathematical inconsistencies in measurable quantities. If a measurable quantity loses its meaning, that's a signal that the model has gone beyond its domain of validity. Now to the point. What exactly is meaningless about Schwarzschild's solution? According to this solution, the square of time near the event horizon becomes zero, and inside the horizon it becomes negative. This means that time turns imaginary. Do you understand what that implies? And this happens when the following inequality is satisfied. Let's recall the expression for local time in the gravitational field of a mass m. If the expression under square root becomes negative, then the time d tau becomes imaginary. What does this mean? It's important to emphasize that in physics, time is what clocks measure. This is the only possible way to measure the duration of real physical processes. There is no other way to give time physical meaning. Absolute Newtonian time, Einstein's relativistic time, and similar constructs are theoretical models used to describe relationships between events mathematically. Their physical reality manifests only through the reading of actual clocks. And those readings can never be imaginary. Imaginary time is an obvious absurdity. After all, we're talking about the physical quantities that can only be measured with clocks. Have you ever seen imaginary clock readings? If so, you should probably replace your clock immediately. Every mathematical expression has a domain of validity. Outside that domain, a formula either stops working or begins to produce meaningless results. This is not just a school rule, but a general requirement for any formula. If we apply it beyond its domain, we get absurd or nonsensical results. The Schwarzschild solution loses its physical meaning precisely at the location of the event horizon, at the gravitational radius. This happens when the following condition is satisfied. Many experts in general relativity, including its creator, have pointed this out. For example, here's what Einstein wrote in 1939 in the conclusion of his paper on a stationary system with spherical symmetry consisting of many gravitational masses. Let's open volume 2 of Einstein's, well known for volume collection, and read. The essential result of this investigation is a clear understanding as to why the Schwarzschild singularities don't exist in physical reality. Although the theory given here treats only clusters whose particles move along circular paths, it does not seem to be subject to reasonable doubt that more general cases will have analogous results. The Schwarzschild singularity does not appear for the reason that matter cannot be concentrated arbitrarily, and this is due to the fact that otherwise the constituting particles would reach the velocity of light. This investigation arose out of discussions the author conducted with Professor Robertson and with Doctors Barkman and Bergman on the mathematical and physical significance of the Schwarzschild singularity. The problem quite naturally leads to the question answered by this paper in the negative as to whether physical models are capable of exhibiting such a singularity. The very creator of general relativity didn't believe in and didn't even allow for the possibility of the existence of black holes implied by his own theory. Moreover, he considered his rejection of Schwarzschild singularity so important that he discussed their mathematical and physical meaning with various scientists. He then wrote a paper publicly distanced himself from Schwarzschild singularities. After all, such nonsense could not possibly follow from his elegant theory. The famous physicist and strong supporter of general relativity, Arthur Eddington, who carried out the first experimental test in 1919, also didn't believe in the existence of black holes. He is what Kip Thorne wrote in his book Black Holes and Time Warps. There should be a law of nature to prevent a star from behaving in this absurd way, that is, collapsing without limit under its own gravity and ultimately forming a black hole. Indeed, despite his sharp physical intuition and his natural ability to sense new ideas in science, Eddington, for some reason, did not believe in black holes. Why do you think that is? By the way, the law of nature that forbids the existence of black holes, the one Eddington alluded to, has already been discovered, and I'll definitely tell you about it later. Now let's open the collection Astrophysics, Quanta and Relativity. It contains papers by leading scientists, experts in general relativity and modern theoretical physics, prepared for the centennial of Albert Einstein's birth. Let's find the paper, The Success and Limitation of Einstein's Theory of Relativity and Gravitation. Its author, Carl Muller, is a recognized expert in general relativity and the author of numerous works on gravitation, theory, and relativistic mechanics. Let us now turn to section 23 and read in English translation. Thus, according to Einstein's theory of gravitation, a system consisting of matter and a gravitational field, initially in a well-defined physical state, may after a finite period of time evolve into a completely non-physical state in which the concepts of space and time lose their physical meaning. Since these concepts enter essentially into the formulation of all physical laws, this would imply a breakdown of physics. This catastrophe occurs when the gravitational field becomes very strong. That is, situation far removed from the case of weak fields discussed in section 20. We are thus led to conclude that Einstein's theory is not valid for very strong fields, an idea that had already occurred to Einstein himself. Under these circumstances, it appears necessary to investigate the possibility of constructing a theory of gravitation for macroscopic matter that retains all the satisfactory features of Einstein's theory, but differs from it in the regime of very strong fields. From the quotes presented, it's clear that the initial attitude of physicists towards the very possibility of black holes was strongly negative. However, by the end of the 20th century, the situation had changed. Most astronomers and even some physicists suddenly began to believe in the existence of black holes. This shift did not happen because they were discovered, but rather due to the constant promotion of these hypothetical objects. It is important to emphasize that not a single black hole has been directly discovered to this day. Astronomers observe only compact, massive objects and indirect evidence such as shadows in radio interferometric images. All of this is interpreted as black holes, but no one has ever observed an event horizon itself. Therefore, it is more accurate to speak not of the discovery of black holes, but only of the detection of compact massive objects that are interpreted as black holes within general relativity. We do indeed observe compact massive objects, but black holes are effectively filled in by supporters of Einstein, who completely ignore his own views on this issue. For now, black holes exist only in their minds, not in the telescopes of astronomers. Why do some scientists believe in black holes? Because they fully trust the Schwarzschild solution and the time equation that follows from it. Why does a singularity appear in this equation? Because it contains a minus sign in front of the gravitational contribution of the mass m. We already know that the unit term 1 in this equation represents the combined contribution of all masses to the timescale, which we normalize to 1. But why is the contribution of the mass m set in opposition to the contribution of all other masses? All the masses of the universe, through their combined gravitational influence, create the unit time scale, but a single mass m begins to reduce it. As an example, suppose m is our sun. In that case, all stars together give the unit term 1, while our star subtracts from it. Now suppose m is some other star. Then all stars, including our sun, contribute to the unit term 1, while that particular star subtracts from it. Depending on the setup, the contribution of the mass m changes its sign, becoming either negative or positive. Thus, the origin of the singularity is an incorrect sign. We discussed this in detail in the video The Sign Catastrophe in General Relativity. It's precisely because of this incorrect sign that the contribution of an individual gravitational mass is set against the contributions of all other masses. I hope you now understand the origin of black holes. Black holes are a theoretical error that arises due to an incorrect sign in the Schwarzschild solution. If the signs in the Schwarzschild solution were consistent, the singularity would not appear. This is a crucial point. In the next video, I will show how to fix all three problems in the Schwarzschild solution. After that, you'll see just how beautiful physics can be. But before that, we'll examine the fourth error in Schwarzschild solution, the most important one. This error completely undermines Einstein's efforts to construct general relativity. I'm Firuza Anchilina. See you in the next video.